Hi everyone, it's my honor to present our newest paper named Towards Designing and Learning Piecewise Spacing Curves by NTU and Peking University. I'm Jianan. First, we introduce our motivation and the main ideas. But first of all, the space-filling curve. A space-filling curve is used to mapping a multi-dimensional data point to a value. Then a one-dimensional index can be used to index the mapped values. For example, the B plus tree index and other traditional indexes, and also the recent learned indexes. Each type of space-filling curve has its own fixed mapping function, and it cannot be adjusted to fit with different datasets. So the idea is that no single SFC can dominate the performance on all datasets and query workloads. Here we give an example why no single SFC can dominate the performance on all datasets. So figure A and figure B gives two space-filling curves. Query 1, the horizontal one, and query 2, the vertical one, are two different queries. In figure A, space-filling curve 1 works best for query 1 that only needs two grid scans, which is grid 7 and grid 8, but not optimal in query 2. While in figure B, however, space-filling curve 2 works best for query 2. So here comes our main idea, is that to design a space-filling curve that combining the advantage of multiple space-filling curves and thus reach to an optimized performance. All right, so in this example, figure C gives a combined space-filling curve, which takes the left half of space-filling curve 1 and the right half of space-filling curve 2. The result space-filling curve, we note it as a piecewise space-filling curve. It works optimal for both queries, which only needs two grid scans for both queries. Now we proceed to describe the problem definition. We assume that the database and workload are given to help constructing the space-filling curve. We studied the problem that developed a space-filling curve function which could optimize the query performance on a given database and query workload. Our method. Now we go to our method. Before that, we introduced the bit merging pattern, which is proposed by Nishimura. The bit merging pattern describes a set of bit merging based space-filling curves. And the idea of bit merging pattern, the input data is first written as the binary form. Then we merge the bits according to the pattern. For example, the XY, also noted as the bit merging pattern of the Z curve. The figure shows how different BMPs merge bits to compute space-filling curves, space-filling curve values. So during the space-filling curve design, there are two desired properties that we would like to maintain, noted as the injection and monotonicity. Monotonicity is desired for designing window query algorithms. It guarantees that the space-filling curves of data points in a query rectangle fall in the range of the space-filling curve values formed by two boundary points of the query rectangle. So during the space-filling curve design, there are three challenges to be considered. The first challenge is how to partition the space and design an effective BMP for each subspace. And the second challenge is how to design piecewise space-filling curves such that two desired properties could hold, which is noted as the injection and monotonicity. The third challenge is how to design a data-driven approach to build the piecewise space-filling curve, given a database and the query workload. So now we introduce our piecewise space-filling curve design. Figure A gives a simple example of our piecewise spacing curve. So in here, we propose a way of seamlessly integrating the subspace partitioning and the BMP generation while ensuring the desired property. So we follow the left to right BMP design and start with an empty string P, and then we choose a bit X. Then the whole space is partitioned into two subspaces with respect to the value of bit x1, where one subspace corresponds to x1 equals to 0, while the other subspace corresponds to x1 equals to 1. This partitioning enables us to separately design different Biot-merging patterns for the two subspaces S1 and S2. So taking the point as an example, it falls into the subspace S1. We then apply the assigned BMP P1 or Z-curve to compute the specific curve value. P1 then compute the specific curve value, and the same way that we compute the point B, the specific curve value of point B with the P2. Okay, so we then introduce the Biot-merging tree. The Biot-merging tree is to model the partition and BMP design information of a piecewise spacing curve. Figure B gives the BM tree, which represents the piecewise spacing curve of figure A. So it is a binary tree where each point starts the selected bit, and the left and right branch of each node means that the bit equals to 0 and 1 respectively. For example, the root node in here starts the bit x1. So the green path corresponding to the space filling curve value computing procedure of point A. We could get the value once the path traversal ends. So now we introduce how to construct the BM tree. In our work, we use the reinforcement learning method. The reason why I use reinforcement learning is that, first, heuristic methods are difficult to be designed to construct BM tree to optimize the query performance for a workload on a database instance. And the second reason is that utilizing reinforcement learning could directly optimize the BM tree based on the reward. So we leverage one of the reinforcement learning methods, the Monte Carlo tree search method, to help us construct the BM tree. So the Monte Carlo tree search method is a good method that it is stable in performance, but is also more efficient compared with other methods, such as PPO. So in this figure is the overall framework of our Monte Carlo tree search-based BM tree construction. It included with 3 steps corresponding to the selection, the expansion, the simulation, and the backpropagation. So now we introduce the main experimental results. So this is the experiment that we compared our BM tree with other specific curve baselines on the Postgres circle. Our method outperforms the baselines such as the Z-curve, quiz, and especially under the school query workload setting. So we also evaluate our method on the recent spatial learn index RSMI. It also outperforms other baselines in this setting. We also show that BM tree could improve the performance of 2 learning indexes, the ZM as well as the RSMI. And we also compare the optimized one-dimensional indexes with other traditional spatial indexes, such as the different R-tree variants. Okay, so now we go to the conclusion and the takeaways. So the main thing is that why the idea of piecewise specimen curve would work. So the design of the BM tree considered a specimen curve set with a larger size, which inherently can contain a better specimen curve. The idea of piecewise also enables the policy to adapt the mapping schemas to different subspaces depending on the specific database instance situation. Okay, due to the time, we will end the presentation here. So thank you very much. If you have any idea, you can just email me or the other authors. We will be more than happy to answer all your questions. Thank you so much.